All right, so are there any questions from previous times?
Sir, in the G theta generator thing, what's the properties of theta and x, and are they real?
Sorry, what context are you talking in?
The generator of SO3, G theta is equal to e to the power theta dot x.
Yeah.
So what are the properties of the x and theta matrices? Are they real?
Theta is not a matrix. Those are the three parameters of rotation. Okay, let me explain that. So G of theta is an element of SO3, and we can write it as G theta is equal to e to the power I theta dot t. So what does this mean? This means theta is a set of three numbers, theta 1, theta 2, and theta 3. And there are some subset of the real numbers. And what they parameterize the amount of rotation in around the axis, around the, say, the x-axis, where x can be I corresponding to 1, or j corresponding to 2, or k corresponding to 3. Okay, that's what theta is. And so theta is a set of three real numbers, and the TAs, or the T's, which are, say, T1, T2, and T3, those are the generators. Okay, so now in previous, when we first talked about SO3, we said that the generators of SO3 should be antisymmetric and they should be traceless, right? But in that case, we had parameterized an element of SO3 in the following way. We had parameterized it to be e to the power theta dot t. But in the tutorial, there is an extra I here. So this gives rise to some subtle differences, which I didn't explain because I thought it would be good for you to discover those yourselves. And these are 3x3 rotation matrices. And therefore, they're real. So if I introduce an I here, but I keep theta real, then in addition to these conditions, Ti is also purely imaginary. And Ti can be given by, I think I gave you that, epsilon. So it's a 3x3 matrix. So it can have, say, two, so it's a JK is the matrix element. And the Ti can be expressed as I. This is the imaginary unit, not the index, times epsilon ijk. Maybe a better notation would have been TA BC is minus I epsilon A BC. So these are matrices. These are matrices, and therefore these are matrices, but these are numbers. And given this expression for T's, I wanted you to verify that TA, TB, the commutator of these two matrices, is equal to I times epsilon ABC TC, which is the Lie algebra of SO3 as well as SU2. Okay, Farhan?
Yes, sir. Last tutorial, I thought theta is a matrix, so couldn't solve the first part. Now I get it.
Okay, all right, cool. Any other questions? Okay, so Nahi also asked a question in the previous lecture about the surjectiveness or onto of the map between SU2 and SO3, right? Nahi, are you there?
Yes, sir.
So I think I've been thinking about it, and the way I would show it is the following. So if I am given some three-dimensional position vector R, I can define X to be Ri sigma I, right? Now suppose that the map between SU2 to SO3 is not onto, okay? So what does this mean is that means there would be elements of U in SU2, which would not map to any element in SO3. So under the transformation of such a matrix U on X, U, X of R would not change, right? Because R would not change.
Under which transformations?
A transformation, so basically, basically an element. Let me just write it the following way. Okay, maybe my logic is flawed. So there is some element, say in, okay, I think I got this wrong. Let me just rephrase it. So there would be some G in SO3, right? For which there is no element in SU2. So that means that G acting on R given X would give me the same X at as this, right?
Why is this, sir?
Because it's we are assuming it's not an onto map. So this is, say, SU2, and this is, say, SO3, and there is a part of SO3 which is not covered by this homomorphism, right? So what I'm saying is that G is an element of that part which is not in the image of SU2.
I think I'm also confused about the last equation. What is this telling us?
Well, it's telling us there is some transformation G, which is which takes us, oh, sorry, this should be R prime. Yeah. Which takes us R to R prime, where R prime is a vector different from R, but which does not, correspond to a transformation in U.
Oh, okay, yeah. So, but
Yeah.
my question is, even if it's not a transformation of U, how can we directly conclude that the transformation should be of this form?
What do you mean? The fact that this is by definition the transformation, right?
Yeah, okay. Oh, yeah.
Okay, so and then I think it's probably should be easy to show that for such a non-trivial G, if G is not the identity, then this is not possible.
Oh, okay, yeah.
Okay.
Wait, sir, I think I'm a bit confused. Like R prime is different from R, right, sir?
Yes.
Ideally. So even if G is not the identity, how can we say that this cannot happen if G R is not R prime?
Right. So yeah, I mean, I have not thought about it very carefully, but I think there are two ways, two things we can do. One is that we assume that R prime is not equals to R. Okay. Then we can show that, this equation doesn't make sense. Okay, this doesn't hold. Okay. The other one would be that in other words, so we have, say, U dagger, right? We want to show that if our map is not onto, then, if R is not equals to R prime, then, there should exist, or, I think I would say if R is not equals to R prime, then U is identity. And I think what I'm trying to say is that if this is true, then, this is not true.
Is X the homomorphism between SO3 and SU2?
No, X is basically the X is just Ri sigma I, right?
So X is
This
a
is
change
what-
of basis, right?
Yeah, X is basically what SU2 acts on. And what I'm trying to say is that there is a G in SO3. There is some G in SO3, a non-trivial G, that is, it is not, so G is not equals to 1, such that, R prime is not equals to R, but, U is 1. Essentially what I'm saying is that SU2 is completely ignorant about this transformation. And I'm saying that that is not possible. Okay, I mean, this is just the idea that I had just before this coming to the class. Why don't you guys see if this can be made more firm, and I will also see that. Okay, then yes.
So I just wanted to ask a question about the assignment. Is that
Yeah.
there was in this question of 1.2, like 2.2 is like we had to construct an explicit map. So by doing the multiplication table and understanding that two multiplication tables are identical, we essentially figure out like a map or the explicit isomorphism. So তারপরে কি আর লেখা লাগবে isomorphism-টা নাকি ওই যে map
Give
multiplication
the
table?
isomorphism between the elements, right?
I mean, like the isomorphism would be captured in the map, right? I mean, the multiplication table, right? So do I have to?
Multiplication table doesn't really make sense unless you give me which which elements map to which elements, right?
Okay.
Right. So, for example, remember that when we did the case where I think it was Z4, and was it Z5 or something, right? But under a multiplication, right? And there, we actually, after constructing the multiplication table, so this was 0, 1, 2, 3, and this element was 1, 2, 3, 4, and then, we actually constructed, I forget what it was, but, we actually constructed the explicit elements map between the elements, right? So you have to, that's something. So I can't remember, I can't recall exactly what.
Okay, I'll include the maps as well then.
Yeah, so, okay. All right. Okay, any other comments?
Yeah, actually, that reminds me, we don't have to show in this question whether or not two of the groups are not isomorphic, right? Because that's a lot of work. You have to show that there's no possible map between the two groups, right?
So which one are you talking about? Which question? Let me bring it up because I don't have it in front of me.
It's the one with the 5 groups, and you have to show which ones are isomorphic to each other.
Oh, I see. Yeah.
I think it is also possible from the multiplication table that it cannot be isomorphic, looking at how the elements are sequenced one after another. And the structure basically comes out from that.
But the one wrinkle to that is.
So a lot of these groups you will see are kind of, cyclic groups, or some of them are cyclic groups, or have subgroups which are cyclic groups, right? So there is some nice property of a cyclic group you can use.
Yeah, that's true. What I was going to say is that there is, if you want to show it from the multiplication table, because you can swap columns and rows in multiplication tables, you also have to technically show that there's no possible combination of swaps of columns and rows that could possibly make the multiplication tables match with each other, which I think is.
Yeah, but you can say the same thing for problem 4, right? Which is there we are also asking you to show that there doesn't exist any isomorphism between Z2 cross Z2.
Right, and I actually circumvented that problem by showing it in a different way.
So yeah, so you can, but for the other problem, you don't have to show that they're, you will basically get some a class of different groups. You don't have to show that these two different groups are not isomorphic. But if you can manage, look, Saif, I think if you can manage to identify that group, then you're good to go, right?
Yeah, that's what I was thinking as well, whether or not I have to actually.
If you can, so for example, what is the group in number 1?
Sorry, I didn't get the question.
What is like the 2 point, the number, the complex numbers? So for example, can someone tell me what is this group under multiplication? What is the name of this group?
Z4.
Yeah. So you know that any other group which is not Z4, which is, suppose you identify some other group to be some other group, right? Not Z4. Say there is a Z2 cross Z2 or something, right? If you identify the group, you're done, right? So if you have say A isomorphic to B, isomorphic to C, and you find C to be some group, some known group, say, I don't know, D35, then you have shown that all of these are D35, right?
Yeah.
Okay, so. Okay, so any other questions or comments?